Okay, our next speaker, Andreas Roeder. He's a networking professional with 2 decades of experience, and he is designing, deploying, and optimizing scalable networks on the layers 2 to 7. Please give a warm welcome to Andreas.
Yeah, I mean, if you want, guys, come close to the stage. Let's have a little bit of fun for, let's say, 20, 25 minutes. I will do a presentation. The whole purpose of the presentation is to give you a brief introduction to Ultra Ethernet. Some of the people are already aware, some already heard it. The goal is basically to enable you a little bit what's that all about. And let's talk a little bit about myself. That's me. We can skip that easily. Just if you want to follow up, if you want to basically download the slides, feel free to reach out, and let's talk. So all of a sudden, no. So one of the questions is why we have even this kind of talk at DENOG. And if you already think about, right now, there's a lot of data center build-outs. There's a lot of connectivity required either inside the data center itself, externally, internally. And you see that a lot of the people with the rise of AI and with the rise of, let's try to use all this kind of GPU resources, question their current infrastructure, question their current design, and think about how to move on. I will talk a little bit about this kind of technology, what basically happened there in the last 15 to 20 years. And then later on, we will bridge a little bit into why this is even relevant and why you should be involved and why I would say you should make an opinion, how you should continue and how you want to continue later on. If you look what happened the last years, and maybe this kind of graphic shows from 2005 what happened all the times until 2023, you see there was a kind of evolution in the data center, but we didn't really have a revolution. So we had small improvements over time, where we started with classical 3-tier kind of fabrics. Everybody still back in the days knows access layer, distribution layer, core layer, and you just configure VLANs all over the boxes, and you try to do that. As long as you never need to troubleshoot that kind of fabric, everything is good, but try to troubleshoot a layer 2 domain with spanning tree, that's not fun. And over time, we basically said, hey, we either need to do something in terms of capacity. That's where lag and multi-chassis link aggregation came into play, where we say, hey, we need to scale that a little bit. So we said, hey, let's have a little bit more of performance. We don't want to have oversubscribed links, so let's go for spine leaf architectures. Then we found a way to build a control plane for all of that and signal our MAC addresses for layer 2 or the IP addresses in a multi-tenant scenario for layer 3, so the entire rise of EVPN and VXLAN, where we also had a little bit of talks about that. But then there was also a big need that we finally need to disaggregate and all of that and involve automation. So you see a constant need over the time that we need to do it, and you reach a point where you say, hey, most likely the last 3-4 years ago, I mean, you reach a point where you build V6 only fabrics. IPv4 and most of the data center build-outs you do recently is not even a discussion anymore. And now we finally need to find a way to deal with AI and ML. But what is really the driving factor behind is this. Because in most of the cases, as soon as we have a kind of technology disruption, as soon as the workload changes in the data center, as soon as you see a new requirement from your compute teams, from your application teams, the work starts. Because now you either have a higher tenancy, more services introduced, more IP endpoints on the compute layer, more bandwidth. You need to deal with that. And the first one was OpenStack, where we basically had a huge rise of VM-based workloads and the entire density of the compute racks started to increase. The next layer was Kubernetes by itself, where you even increase that further and you go from multiple 20s per server to hundreds or even thousands per server in terms of density of endpoints. And now a really, really, really big shift was from 21 to 22 when a company called OpenAI released something to the public called ChatGPT. And everybody say, hey, now we need to do something with this AI stuff. But this has a lot of impacts to the data center design. Another way to think about that is that. So if you see here on the left side, that's a very classic kind of architecture. You have a data center interconnect, and again, this is simplified. You have a spine layer, you have a leaf layer, and you have your CPU-driven server. This CPU-driven server is very important because back in the days, CPU was basically the bottleneck. It was all about CPU cycles and how you can either offload that and how you can do that. On the right side of the slide, you see what you need to build these days. First, there is a demarcation where you don't build a single converged fabric anymore. In most of the cases, these are either two fabrics, and later on I will explain why it's not even two. Sometimes it's even 4 or 5 different fabrics. And then you have something, and it's called very often differently in the different marketing lingo and in the different companies. It depends a little bit who released the white paper. But everything where the user connects with the data center is called the front end. And everything where you have basically your GPU to GPU communication, those kind of things, is referred as a back end. What you also see on the slide, indicated by the colors, is basically that you use a different technology. The front end is basically maturity, Ethernet, everybody, what we do as an industry for the last 20 years. On the back end, and for the people who are potentially familiar with HPC clusters, they know this technology quite well. This is driven by InfiniBand and InfiniLink, because therefore everything is about connecting GPU memory to GPU memory. You want to write from the memory from one GPU to another GPU, and you see that. So this breaks your technology domain, because at a certain point you realize, well, I now have 2 different competing transporting technologies in my data center. How to deal with that? What do I do with that? And how I even manage all of that? And then you want to go from there, and sorry, the contrast doesn't really look that more smart, to this. And that's basically the goal of this kind of presentation, because the transforming technology to replacing InfiniBand in the back end is called Ultra Ethernet. Because I will talk a little bit what do you need for that, and what are the semantics of it, and what are the driving factor. Just to outline a little bit, once you solve that kind of puzzle, that's basically one of the most final stages you can reach. Each of the bars is representing a single fabric by its own. In most of the cases, that's how a typical AI-driven cluster architecture going to look like, where you have front-end management, storage totally separated. So each of them has their totally independent fabric. And then you also have the back-end architecture. Can be based on Ethernet, don't need to be, but these using also totally different topologies. For the people coming a little bit from the HPC cluster, this is all based on Rails, where you basically say everything is a single hop away. Very important. But this more as a reference. So what is Ultra Ethernet? Ultra Ethernet is basically a consortium of various companies. They came together and say, OK, let's try to agree on a common standard on the overall evolution of Ethernet. And let's try to define it, and let's move Ethernet as a standard to the next level. You see a lot of different logos in there. I mean, it's mainly driven by all the different OEM vendors, transport vendors, compute vendors, chip vendors. So there seems to be a kind of consensus. The interesting thing is, even if it was set up initially to compete with NVIDIA, because InfiniBand is licensed by NVIDIA, and that's the only supplier on the world who gives you that, they are part of the Ultra Ethernet consortium, because obviously they want to listen and they want to see what's going on and they want to potentially compete. Why is this even relevant? And what's the problem we try to solve? So if you see typical HPC clusters or AI clusters, they are all driven by GPU to GPU communication. So you basically write part of your job from one GPU to another GPU. That's called remote memory access, RMA. And what you basically want to do is you write straight into the memory, and you bypass any kind of kernel, any kind of OS, because it needs to be really, really fast. And just once the information is delivered to the GPU, the job can start, you do all your calculations, you finish the job, you give the results back. So you want to have really fast job completion times, and the way to do that is GPU to GPU. There's one standard or kind of protocol which is called RDMA over IP, where the people said, hey, yeah, InfiniBand is fine, but I want to at least have the same transport layer, so please keep at least my IP. So you basically do it via RDMA over IP. The standard for that is Converged Ethernet v2, so Rocky for the people who can follow that. In contrast to that, you have the Ethernet ecosystem. So everything is almost there, right? You have your tooling, you have your operational experience, and you know what you do. But nevertheless, there's a sum of things where the current implementation of RDMA lacks. You don't really have the possibility to have multipassing in the system. So it's a very concrete path everybody needs to follow. And there is really a or you cannot really have the possibility to deliver unordered packets. So everything needs to be either in the right order or you need to buffer it. And it's very hard to do. I will skip about that one. It's just for marketing. The focus of Ultra Ethernet these days is the entire scale-out scenario. So basically, you have multiple racks, and you want to combine that together in a single data center. There is some references which call scale-out between data centers, scale-across, but I will skip that for today. One of the goals, and you already see that they try to address some of the shortcomings from the current RDMA implementation, is we want to have multipassing, so we want to have the possibility to use multiple routes. We want to have a little bit of congestion control. So in case something is either stuck or I want to signal any kind of congestion, I want to have mechanisms in place who do that out of the box. I want to at least try to get it lossless. I don't want to have any kind of retransmits. I don't want to have any kind of lost packets or lost frames. So let's try to get that as lossless as possible and implement it. There is also the goal from a design perspective to integrate security, but to be fair and honest, as of now, there's not much which happened yet. So basically, the people come together. We as Nokia are also obviously part of that kind of consortium and have a contributor. All of those kind of references, you see it right here, the sources are already there, so I just give you a kind of quick dump of the reference sheet, what this is all about and how all the different pieces belong together. But what they have basically done is these are the kind of different layers we need to talk about it. There are some of the important layers and some of the less important layers I will highlight in the next slides, because the majority of the innovation and the majority of the changes are done in the transport layer. And for all the people who are quite familiar, which I assume the entire room is, with OSI, I mean, it's exactly the same kind of layout. You have 7 different layers, 4 is the transport, and that's what you do. What you see here, there's a big difference because inside transport, there are 2 categories which are now part of it. One is the so-called packet delivery. So that's all about how to move packets from A to B, how to deliver them, and how to make sure that we get this kind of lossless operation and we get towards the goals. And the other one is congestion management. So if I really get stuck, if really happens something, what to do about it, right? That's a really nice one, because this indicates basically what you reuse from existing technology and what you change. So as you see here, the green, these are the kind of stuff which already existing, right? There's a software layer for the people who are coming a little bit from AI and so on. This, in majority of the cases, it's either nickel or RICL, which is just a fork of nickel, but it's a de facto standard. Then you have the transport layer. That's obviously the blue stuff, where the majority of the innovation and change actually happens. Then you have the network link, physical, but you see a lot of green stuff, which just exists, and which is augmented by optional stuff from the UEC. But that's not really super critical to make it work. How it works, so all the sub-layers are basically inside there. From a stack perspective, so the usual stock, we as an industry try to tend with every new kind of thing. We build just another envelope, we build another encapsulation, and since IP UDP is cool stuff, then let's use that as our transport and put all the other stuff on top. That's what you also see here. So you have basically normal Ethernet frame with an Ethernet header, IPv4, UDP, and then all the blue stuff, which is Ultra Ethernet transport, starts to come in, and you have the different layers right over there, which basically stops with an FCS, and then you get forward. That's very important because this allows you basically to reuse same what you do with EVPN, VXLAN, and normal forwarding based on IP from a control plane perspective and just put the stuff on top of it. This is very important because where you see all the different innovation right now from a packet delivery subsystem. So it's what they basically say is we have from the software layer here indicated on the left side of the slide to the hardware layer here indicated on the right side of the slide. This is how the packet will flow inside the system. I will not go into any kind of detail because it just should give you an idea on how to group things together, because now obviously transport, congestion management, and also security is one piece together, and everything is done on exactly the same header. This is just a comparison on Rocky v2. So what we said before, this is the kind of protocol. And as you see here, IB stands for InfiniBand. So that's what they basically use inside to make that protocol work. And one of the goals is to simplify that a little bit with UET transport. And you have there the possibility to use inside the RDMA layer, which modules that. Now, coming to the kind of not so trivial part from a networking perspective. Because what we said before, everything was flow control and order was very important. These days, we skip that completely. Because what you introduce in the packet delivery subsystem is basically 4 different transport modes. And out of the 4 different transport modes, the unordered is the one where people get really excited about. Because you don't really want to take care anymore if packets are in order, and if they need to be stored or if they're transported in the right direction. We want to make use of the unordered stuff as much as possible, and you see that it's basically I would say almost the de facto standard, and a lot of implementation rely on that. What's also very important, we had this before in the industry, we need to identify the packets. So what we basically do is we stamp each of them, and everybody gets a kind of sequence number. We will reuse that later on, because what you can do, if you can identify the packet by a unique identifier, you can basically say, out of the flow, I don't care that much, but just give me that kind of piece of information back. Just resend that particular piece outside of the protocol, which is very important. Also from that regards, there's a difference between basically byte stream based or flow control. And the best explanation is basically, if you think about in the traditional kind of fabric, that's what you use in front end, you would always use flow. You basically have your NIC, you have your switch. The switch says, this is my table, I build a hash on this kind of flow, I build my next hop, and then fire and forget. And everything which matches this kind of flow follows this kind of distinguished path. We don't do that anymore. So we take a NIC and basically say, take all the ports you have and start to sending all the different packets across all the available ports. This is basically referred as packet spraying, where you say, whatever comes, take one free link, shout out the packet, and send it to the destination. Another packet delivery principle, which we said before, you basically use the identifier, you're using the sequence numbers, and basically said, hey, I want to simplify all of that. One way would be from a traditional 3-way handshake. What you establish, we're eliminating 1. So you basically send that with the first packet, similar to what you do with other protocols. And you see some of the technologies for the people who follow a little bit higher stack protocols like Quick and so on. Some of the ideas are also reused here and brought down to Ethernet. It's quite similar from a technology perspective. This is something I already discussed before, where you can do selective retransmission. You don't really need to say, I want to get the entire flow back. I don't want to get the entire packet back. I just want to get this particular piece, right? Please give it to me. As highlighted before, and this is just a usual representation of a flowchart where you can say, well, how is packet spraying really going to look like, right? think about, on the left side, there's your switch, and these are the different packets on the wire, which you can utilize, right? Versus I use whatever comes, and I don't care about order. And one of the technologies which allows me to do that, because obviously people would say, well, if I don't care about order, how to make sure that the receiving side can even work with that? But think about the use case again, right? What we want to do is we want to write from memory of a GPU to another memory of another GPU. So what we also do inside the header, we just give it straight the GPU address. So therefore, packet order don't matter anymore at all. You basically have a direct target where you just write, think about an envelope street address where you deliver every packet. And the job of the GPU will anyway just start if the last packet will arrive to be complete. So order don't matter in backend fabrics anymore at all. This is just a highlight where you see there is a little bit of ideas from the community and so on, where you say, well, if I really need to reorder, if flow-based is really a thing and I want to reuse this kind of technology, this job will be pushed to the NIC. And there where you see a lot of, for people who follow a little bit the NIC market and so on, there's a lot of innovation like Tor from Broadcom, where you basically say, okay, the major difference between normal NICs and this kind of NICs is just the amount of buffer and queue sizes, because you need to store all this kind of stuff in order to be able to reorder. We talked a little bit about congestion management. As you see, there are two very important things where you say, okay, how to deal with congestion in case it will occur. One of the goals is to avoid it as much as we can. So therefore, there are two technologies fully integrated into Ultra Ethernet. One is basically where you say, I want to have the possibility to react on the server side. So if I feel, hey, I'm congested, is there a way to signal back to the originating sender, hey, I have a problem. I either run out of queue, or I don't have a problem or I have a problem to deal anymore. And there are multiple technologies integrated right over there. The most common one used is Econ, where you basically say, I have a way from the receiving side to the sending side and say, hey, I run out of queue. Please stop sending. And so those kind of messages are very important because they will traverse back from the receiving side to the server side. And you can also use this in intermediate hops. Will not be that much the case because, again, like I said before, if you have a rail, it's only one hop. There's only one switch port in between the GPUs, so therefore it will be a receiving and resending story. But Econ, very important to follow up. That's the kind of technology which needs to be supported. The other one is basically where you say, why not giving out at the start of every conversation kudos? Everybody gets 10 credits. If you send me a packet, you burn 1. If this packet comes to the other side, I give you back 1. Because now you have another 10 packets and you can send. As soon as you run out of packets, it means me, as on the receiving side of the house, haven't received the packet, and you don't get anything back, so you cannot send it anymore. So that's an implementation which is also implemented very much, and both of this kind of mechanism are used in parallel. What are we trying to achieve? Very easy. I mean, that's basically, if you look into the InfiniBand problem, that's how it looks like. That's what you can consume. And the idea of the Ultra Ethernet Consortium is basically that we go in and say, it doesn't need to be Nokia. And to be fair and honest, in a lot of those kind of buckets, we are not even present. But we want to give you, as a customer, options. We want to discuss about consumptions, and everybody can build their own ecosystem, and everybody can build their own pieces and puzzle out how to bring things together. That's the goal of this entire technology, and how to do that. And what we also believe really strong as a vendor, and this is most likely the only marketing slide I really have, without calling it out, we strongly believe in Ethernet because, as you see, I mean, there's a lot of things which come over time where we boosted up Ethernet as a technology. Coming from switching, going to routing, having integrated timing, having things like synchronous Ethernet, having another mechanism to do quality of service on top of it. So therefore, we really believe that Ethernet is here to stay. It's a technology which gives you choices, which has the broadest ecosystem right now, and where most of the people have the skills to operate it. And Ethernet will also scale. I mean, if you look right now, we have bandwidths which reach closely 1.6 tera these days in a single interface. So therefore, it will be ready and it can power up the data center of the future. And now, that's the end of my talk. Happy to get any kind of questions, feel free. And I hope you get some kind of impression on what the future might gonna look like with Ultra Ethernet. Thanks.
Thank you for this very interesting talk. Are there questions?
Stefan, yeah, private person. Is there any interoperability lab in Europe where you can test this stuff?
Yes, there are. I mean, first, there are a bunch of implementation from different vendors. There is a goal to do it in the next EANTC MPLS Congress. Nevertheless, we wait for some of the vendors to do it. What we have done, which is, sorry, no marketing, but it's public press, where we did external testing authorities with an external tester, and we basically said, this is the 800 gig connection. Please test it. And the results are quite interesting because the overall job completion time and the overall performance was even better than with RDMA Rocky V2.
So, Stefan again, you mentioned IPv4 and IPv6 in one of the slides. Which is the preferred one?
If you ask me personally, IPv4 is not even a discussion anymore.
Thank you very much for this awesome statement. Please, a warm applause for this talk. Thank you.